class, we're going to be looking at the quantum model and electron orbitals. So now things are going to start getting a little bit more complicated. Yes, more than they already are for some of you, because some of the concepts, this is new and it's sort of hard to understand in the beginning, but keep with it. It'll eventually start clicking in. It's the beginning with new information. So the Bohr model helped to describe chemical properties for some elements, but not and the concept of energy levels. However, there was limitations to the Bohr model, and it failed to explain many important properties such as behavior of the transition elements or the complex line spectra of elements outside of the hydrogen element. So now we're going to get to Heisenberg. Next we're going to look at the quantum model. And let me go back one. So the quantum model, which describes electrons and particles as waves. So, excuse me, let me start back. It explains electrons as particles and waves. So there's a duality of the theory here. This is a part of quantum mechanics, the study of unique behavior in subatomic particles. So what does this mean? Well, simplistically, the easiest way for me to explain this is that what they found is that electrons behave as particles and it behaves as waves. So in some circumstances, it behaves strictly as a particle, and in others, it behaves strictly as a wave. So now they have combined and taken the information that they have gathered, and this is where the particle-wave duality comes from, is that they can explain certain situations when it pertains to a particle, and they can explain other situations when it pertains to a wave, and they combine it, and they can describe the behavior a lot better. So that's as simplistic as I can explain it. We're not going to delve too much into that more than what you're reading and what you learn here on the quantum model. Heisenberg uncertainty principle. So Heisenberg is not just, if you watch Breaking Bad, that's the name that he uses in it, if you guys have ever seen Breaking Bad. 1927, German scientist Werner Heisenberg put out an idea of the uncertainty principle. And now this is a part of the quantum model, quantum mechanics. And what this is the uncertainty principle. This principle deals with mass, velocity, and the location of subatomic particles. The key idea of the principle is it's impossible to precisely know the exact velocity, which is the speed, and the location of the particle, meaning electrons. So remember, you're dealing with, and if I haven't stated it, you're dealing with a tiny, very fast-moving particle. So you can't always see, and we're not dealing with things that we deal with every day that we are big and we can locate them. We're dealing with stuff that we can't see with our eyes. So the easiest way to explain this is that we don't pinpoint location. We describe a probable location of the energies based on information, based on experiments, based on data gathered. So this isn't just guessing. The easiest way to explain it is if you look at the fans. These fans have 3 fins to them, and when they're not on, you can say, okay, that's 1, 2, and 3. There's 3 blades to this. However, when you turn it on, you can't pinpoint exactly which fan is where because it's moving so quickly. But you can determine the shape, and as it starts circling, you can see that it's kind of like a spherical shape, a circular shape is what I should say. And so this is very similar to finding where electrons are located. We can never say with complete accuracy, we know that an electron is located at this corner in this spot, but we can tell you based on statistical information, the most probable locations of where electrons are located. And that's what we'll do. So if we look at a fan, we can take that circular shape as it's moving and say, well, it's highly statistical that an electron is going to exist in the blue portion of that moving fan blades compared to outside of it anywhere over here. It's not probable, most likely not going to find an electron out here. That's how we now describe looking for electrons. And that's going to now affect shapes. So I took these slides from another course, and I'm trying to break it down a little bit easier. The Bohr model was replaced with a more sophisticated model called the quantum mechanical or wave mechanical model. The quantum mechanical model of the atom replaced the Bohr model in the early 20th century. It states that Bohr orbits were replaced with quantum mechanical orbitals. We're going to cover the orbitals. Orbitals are different from orbits in that they represent the probability maps that show a statistical distribution of where the electron is likely found. That's exactly what I'm saying, is that based on information, there's a high probability of where they think an electron exists within a certain shape, and it's most likely not going to be found outside of that. Quantum mechanics revolutionized physics and chemistry because in this model, electrons do not behave like particles flying through space. We cannot in general describe their exact paths. We look at more shapes. An orbital is a probability map that shows where the electron is likely to be found when the atom is probed. It does not represent the exact path that an electron takes as it travels through space. So we won't know the path that it took to get where we think it's probably at, just that it's probably there. Okay, so wave nature of electrons. Second principle of quantum mechanics. So the first thing is that we don't know the probability of, one, we're going to look at it as a wave. We're going to look at these as wave, and the probability of knowing a location, not the exact precise location, but probable location is based on shapes. Okay, so here we're going to look at, up until this point, we refer to electrons as particles. But now we're going to look at their behavior is more closely resembling energy waves. The aligned spectra shows electrons only exist at certain energies, and Bohr stated only certain energies were allowed, but really couldn't elaborate as to what was going on with them. But what if electrons behave as waves, similar to a guitar string that oscillates at a very specific energy? So in that case, by treating electrons as waves, quantum mechanics are able to explain why electrons only exist at specific energy levels and predicts the energy changes produced from line spectra. So this is more of a physics thing. We're not going to go really deep into this, even with the math or equations, especially not at this level. But that's pretty much it, is that we focus on this new model of looking at stuff. Okay, so the quantum model. There's two main ideas. The uncertainty principle, that's the first one, where we can determine the probability of where an electron is, but never the exact location. And it's based on statistical data that we have gathered. And the other one is the wave nature of electrons gives a foundation of our modern understanding of electronic structure. So quantum, they put QM, quantum mechanics, or the quantum model, describes electrons by energy and probable locations. We do not try and pinpoint the location of electrons. We talk about the energies of electrons and the electron waves and the regions around the nucleus where the electrons are most likely to be found. Look over the rules that govern the configuration of electrons within an atom. So we're going to look over the rules that govern, and we're going to cover this. This is the majority of the slides are now. We're going to start looking and breaking down stuff. Okay, so first we're going to start with energy levels. Now again, this is where I'm telling you, just stick in there, hold on. Some of this may seem really overwhelming and extremely confusing, but it will start making more sense when we get to the next section. I'm just presenting it to you now. And with the next section, I think it will click. It's just something new and foreign, and sometimes this stuff is really difficult. Chemistry is known to be difficult, and this is why. Trying to understand something so foreign in a small amount of time can be difficult, but it is not impossible, especially if you put the effort in. Okay, so to describe the arrangement of electrons within an atom, we start with 4 foundational rules. 1, this is the first rule. Electrons occupy different energy levels. The energy level is identified by a whole number called the principal quantum number. That is the number that you see. It's 1, 2, 3, 4, and here is a hint that your book doesn't tell you. I will discuss it in the next section as well. It matches the row number, the row on the periodic table. Remember, there's 7 rows. So if we start looking at elements located on a periodic table, the main quantum number is going to match that row number. So n equals 1, n equals 2, n equals 3, n equals 4. Higher energy, okay, so the lowest energy level is level 1. It's closest to the nucleus. So that's the lowest energy. Higher energy, and we start at the bottom. So think of this as a bookshelf, and you cannot just put books randomly. You have to start at the bottom and fill it up. but there's certain rules to how many books can be on each shelf. And that's exactly what we're looking at here. So we start adding books at the bottom until we reach that max that it says it can be there. Then we add to this one to that max, and then we add to this one to that max until we add, and we keep going. So that's how we look at this. We don't start with, even though this is level 1 here, level 1 is really at the bottom because it's the lowest energy. So lowest energy level 1 is closest to the nucleus. Higher energy levels 2 then 3 lie farther from the nucleus. Higher energy levels can hold more electrons than the lower energy levels. So level 1 can hold 2 electrons. So if I tell you this in terms of books, this can hold 2 books. Level 2 can hold 8, level 3 can hold 18, and level 4 can hold 32. So if that's a simplistic way of explaining this, okay? Trying to make it as easy as possible, but some of this information is just a little hard. Okay, so rule 2, each energy level contains 1 or more sublevels. So what does that mean? Well, let's pretend we had a bookshelf. Let's go back. And in this bookshelf, we had sections. And we call these sections sublevels. That's what this is saying, is that we break these up into not one whole shelf, but how about we broke them up into little shelves, and each shelf is named a sublevel with its own name. That's what we're talking about now. So if we're on n equals 1, we have a sublevel that's called S. And then what if we had it on the next one, we had S and P. We broke it up and we called this shelf S and this shelf P, but we're still on the level 2. So that's how we're breaking it up. And this is where I told you things are a little harder to understand. Don't worry, keep going. Okay, so each energy level contains 1 or more sublevels. There are 4 common energy sublevels, and they're designated S, P, D, and F. S is the lowest, F is highest. Each sublevel can hold a set of electrons. So let's go back to this bookshelf. We start at the bottom, we start loading. Now, what if we broke these up into sublevels, and now we have to add based on the order and the rules and how many? So that's the same thing here. We have sublevels. I have to add on this one first before I can add this one, and I can only add a certain amount. Then I have to go to this one and add this one, and then this sublevel. And when I reach this filled sublevel, I have to go to the next one. So hopefully it makes a little bit more sense as to what we're dealing with. So each sublevel can hold 2 electrons. And it doesn't matter what level it is, there's a certain amount of electrons that it can hold. Okay, so each sublevel contains 1 or more orbitals. So an S sublevel contains 1 orbital. And let me see, I'm looking at something here. Okay, an orbital, each sublevel contains 1 or more orbitals. An orbital is the region where the electrons are most likely to be found. This is the probability location. Each sublevel contains a different number of these orbitals. So S contains 1 orbital, P contains 3, D contains 5, and F contains 7. Okay, so now let's take a look at the Bohr model and the quantum model. Difference between orbits and orbitals. So the Bohr model describes electrons as particles orbiting the nucleus, like planets around the sun. The quantum model states we never know the actual location of the electron. The term orbitals describes the region around the atom where the electrons are most likely to be, and this is based on statistical information. So think of this as these shapes to tell us this is where an electron most likely is, and being outside of the shape is where it most likely isn't. So it's a probability factor, and these things are constantly moving, so we can't just hold it and say this is where it's at. They're moving at a speed that is very, very quick. So not in orbit, we're discussing orbitals, and these are the regions that are most likely where, based on information, an electron is located. Okay, rule 4. Each orbital holds up to 2 electrons. So each orbital, now if we go back to orbitals, S sublevel has 1 orbital, P has 3, D has 5 orbitals, and F has 7. Now each orbital, 1 orbital can hold 2 electrons. So an S sublevel can hold 2 electrons. A P has 3 orbitals, and each orbital can hold 2. So that's 6. D has 5 orbitals, and each orbital can hold 2. So that's 10 electrons that can be held. And F has 7 orbitals, and each orbital can hold 2. That is 14. So I'm going to cover that again. Each orbital holds up to 2 electrons, and electrons have a tiny magnetic field called a spin. So think of magnets. Remember when you try to put 2 positive ends together or 2 negatives, they repel? Same thing with electrons. They have a magnetic field. So in order for them to be paired, you have to put the charge, the north and the south poles opposite. So we draw them as arrows, like these half arrows. And this points up and this points down, which is similar to the magnets. And that's how they are paired in an orbital. So they are paired with opposite spins together. If you pair these with the same spin up, they are very unstable. So an orbital is filled if it contains 2 paired electrons. You can never add more than 2 electrons in an orbital. That's it. Think of a bookshelf. You can't have more than 2 books on a bookshelf, and one has to face this way and the other one has to face that way. That's how you think of these. Okay, so this is a summary of what we're just covered. 1, electrons occupy different energy levels. Each level contains sublevels. Each sublevel, so sublevels are S, P, D, and F. Each sublevel contains orbitals in it, and each orbital holds up to 2 electrons. So simplistically, as I can try to explain this, this is like an address. We're trying to find out where you live, and we can get down to your address and your house, but I can't tell you exactly what room you're in because I can't see you in your house. And that's the probability is, let's say if it's 11 o'clock at night, there's a high probability you're probably in your bedroom, maybe sleeping. Maybe 3 in the morning you're sleeping. This is the probability. If it's 12, maybe you're at 12 in the afternoon, high probability, maybe you're in the kitchen making lunch. These are the things. So we can pinpoint everything down to maybe your house, but then we can't tell more than that. But there's a high probability you're in your house and a high probability you're probably not in your neighbor's house or outside in their yard. So if that makes sense. Electrons, okay, so let's go. Each sublevel contains orbitals, that's 3, and each orbital holds 2 electrons. So if we look here, a level 1 contains 1 s orbital, and each orbital can hold 2 electrons, so that can only hold 2. P has 3 p orbitals, and each orbital can hold 2, so that's 2, 4, 6. D has 5 orbitals, 2, 4, 6, 8, 10. Can hold 2 electrons in each orbital, so that's where 10 comes from. F is 2, 4, 6, 8, 10, 12, 14. That is 7 orbitals. Each can hold 2 electrons, and it can hold up to 14 electrons. Okay, so now, your book gives you these pictures, but I think it's easier to explain this with a slide that I took from other ones. So remember, this is a probability, and what they did based on the information is they are able to take statistical information of where electrons exist and then determine what that shape looks like. And the shape is the highest probability of finding an electron in that shape and the low probability of finding it outside of that shape. So, and it's on the XYZ axis. So this is from another book. And the dot density and shape representations of the 1s orbital. The dot density is the proportional to the probability of finding electrons. So based on data, this is what they've come up with. The greater dot density near the middle represents the higher probability of finding an electron near the nucleus. So then they create a shape because of it, and then you can see it superimposed. So when you're seeing these shapes, there's actually based on data gathered, and they create the shape to show that. So a level 1 has only 1 orbital, and it's S, and it's a spherical one. And this is the probability of finding an electron in this. Level 2 has an S and a P. So this shows the 1s orbital here, and then there's a bigger 2s orbital that's also spherical because S is a spherical shape. And that is right here. So I took one from my other slides, and you can see the 1s and the 2s is bigger, and it just overlaps it. Level 2 also has p orbitals, and they look like the infinity sign, and you can see there's an x goes across the x-axis, y-axis, and z-axis, and if you put it together, it looks like a whole bunch of balloons tied together. This is from other slides, and I just want you to see the dot density to show you where they got this information from to create these. You don't need to worry about the px, py, and pz. You'll learn that in Chem 24A. But that's actually what these are called, because this is on the x-axis, this is on the y-axis, and this is on the z-axis. and there are 3 p orbitals. So this can hold 2 electrons, this can hold 2 electrons, and this can hold 2 electrons, and that's where the 6 electrons come from. This can hold 2 electrons with the 2. So that's a total of 8 electrons from the 1 orbital in the level 2. We're looking at only level 2, and then the 3 orbitals, and that contains 6, so a total of 8 electrons. Now we look at level 3. Level 3 has excuse me, s orbitals, p orbitals, and d orbitals. And the d sublevel, so these are d orbitals. So each level they have, so for level 1 and level 2, at level 1 the s orbitals are all spherical. P orbitals, they look like dumbbells. Doesn't matter what level they are actually. So if we go to level 3, they also have p orbitals. They're just bigger, very similar to this. And then d orbitals are the ones we haven't looked at yet. And these are 5 orbitals, and each of these orbitals can hold 2 electrons. Don't get too worried about the shapes for d orbitals or f. Do pay attention to the p's and the s's, though. This I'm not going to, these are just crazy. I don't even know how to explain it, except for maybe this one looks like to me it's always looked like a pacifier in a sense. But so d orbitals and f orbitals, they all look very complex. I'm not going to ask too much about them, but you definitely should know what p orbitals look like and s orbitals. And they look the same for all levels. They just get bigger as the energy levels go up. Okay, so where does this come from? So with level 3, we have an s orbital. That's 2 electrons. A p, we have 3 again. And d, we have 5 orbitals. That's a total of 18 electrons that can be held on a level 3. Let's look at level 4. These are f orbitals. They are even crazier. I don't even know how to explain these. So now we can hold 14 electrons in the f sublevel. So a total of 32. We have an s orbital that holds 2. P orbitals that have, there's 3 of them, can total electron capacity of 6. D orbitals have 5, electron capacity of 10, and f orbitals have 7, so electron capacity of 14. That's a total of 32 electrons that can be held on level 4. Okay, so here is a summary of everything that I've just discussed. So E with the minus symbol means electron. So if we look at level 1, we have an s orbital only. It can hold 2 electrons. If you go to level 2, we have an s orbital, and we fill, remember, we fill at the bottom up. That's why I'm starting at the bottom. We start at the bottom bookshelf and fill up this way. So we have, for level 2, we have an s orbital, which can hold 2, and we have 3 p orbitals that holds 8. For level 3, we have an s orbital, holds 2, p has 6, and d has 5 because we have 10 electrons because we have 5 orbitals. That's a total of 18. And then f, we have s orbital, which holds 2, p orbitals, there's 3 of them, holds 6, d has 5 orbitals, which hold a total of 10, and f has 7, which hold a total of 14 electrons. So that's where the 32 come from. Again, may not be making sense. Will make sense after we complete next section. So here is another thing to pay attention to. What does all this mean in a sense? Well, we are looking at energy levels. And this is a diagram of energy levels. This is how it's set up. This is how you're going to pretty much learn it. Diagram shows the relative energy differences between the energy levels and sublevels. Within an energy level, the s orbital is the lowest in energy. You can see here are the s orbitals. If you see with 2s, it's below 2p, 3s is below 3p, 4s below 5p, 5. So it's lower in energy levels. S orbital is the lowest in energy. It's followed by p, then d. So we see all p's, then we see d's, and then we see f's. As the energy levels get higher, they become more closely grouped together. And as the energy levels branch out, this is branching out this way and branching out this way, into more sublevels, they begin to overlap each other. And so one thing I want to point out here is energy level 4s is actually lower in energy than 3d. And that's a trend that continues. 5s is lower in energy than 4d, 6s is lower in energy than 5d, 7s is lower in energy than 6d. That's a trend that stays with this once we get to 4s. This is from another one of my books. I just wanted to have it where you can see and count everything and it spills out. This is the way the energy levels are, how they're set. But this, you can visually see how many orbitals. So if I add 2 electrons here, it's 1 and then 2, 1 and 2. So this kind of helps when you're first learning how to do this. Okay, this matches exactly what I showed you on the previous page. This is filling order. What is filling order? Well, filling order is basically this. It's just more condensed. This is how you fill it up with electrons. You start here, 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 and we start going up. 4s is lower in energy than 3d. 5s is lower in energy than 4d, and it continues. Okay, so let's ask some questions, and hopefully this makes sense. What sublevels are present in energy level 2? So let's take a look at 2. Energy level 2, we have an S and a P. That can hold 8 in total. So let's just cheat, and it's B. Which of the following does not exist? Okay, so let's see what we can't find on here. So 1s is here. 2s is there. C is 2p. Well, 2p is here. D is 2d. No, we do not have a 2d, but we do have a 3p. So 2d does not exist. There is no energy level 2d. It goes straight to 3s. An atom has 12 electrons. The highest energy electrons occupy which sublevel? So this is what I haven't exactly, I kind of mentioned it maybe. I hope I did. This is filling order. I'm given 12 electrons. I start at the bottom. I fill the bookshelf up. And I can only add 2 electrons to each dash, which is considered an orbital. So let's just fill them up. So let's pretend this is 2 here, and 1 goes up, 1 goes down. 2, 4, 6, 8, 10, 12. So its highest energy level, I can't even speak. Its highest energy electrons occupy which sublevel? So I am going to cheat and tell you, yes, we filled it here. 2, 4, 6, 8, 10, 12. It was a 3s sublevel. That's where we stopped filling it up at. This is filling order. This is exactly how we're going to fill up electrons. Which sublevel can hold up to 10 electrons? So remember, sublevels are SD, SP, D, F. So if we go, we can see that S can, nope, P has 6, that's 2, 4, 6. D, 2, 4, 6, 8, 10. It's going to be D. And it doesn't matter which D because 4D also does the same. So D orbitals can hold up to 10 electrons. Which of these statements reflects Heisenberg's uncertainty principle? Electrons are best described as waves. Yeah, that's part of quantum mechanics, but it's not Heisenberg's. We never know the exact location of electrons. That is true, but we need more information than that. Electrons fill the lowest energy levels first. That is also true, but that doesn't have to go with Heisenberg. Electrons occupy S, P, D, and F sublevels. And the atomic dog chases Schrodinger's cat. Schrodinger's cat is something you will learn if you continue on with chemistry. If you watch Rick and Morty, there was a Rick and Morty episode about it. I'm not even going to touch it. Anyways, electrons occupy S, P, and D, F sublevels. That is the correct one because Heisenberg's uncertainty principle has to do with we have the probability of knowing where an electron might be, but we cannot say with accuracy that's where it is. This is where the S, P, D, these shapes come from, where based on information, we have a probability based on the shapes and the probability of where it's not based on the shapes. This is Heisenberg's uncertainty principle. That goes